Hello, I'm Roman, and welcome back to the series of the videos Neural Networks from scratch in Go. And I don't know what's happening today, but I'm trying to record this video a third time already. So the first time I started to record, I needed to interrupt because I needed to do I need to help. Second one, I actually recorded the full video and for some reason the OBS, it happens from time to time, but OBS did not record the screen. So it recorded me like from the camera, but the image from the laptop stayed the same. No idea what happened, but I mean, and I wouldn't say that's really bad thing. I mean, from what I did during this video is I actually started from previous chapter where we took a look at how to calculate the partial derivative for one neuron having one single input, but then it continues and it expands and gives an idea of how to calculate the partial derivative for, well, first for the layer of the inputs. I think this is the one, and I will just make a short summary here, and well, for you and for myself, just to learn it through. So we need to have for example, for one neuron we have a gradient with values, and for the layer of the neurons we need to have the same, well, not the same, but the same one-dimensional array of the gradient. And in order to do this, we will have the gradients for all of the neurons within the layer, and then we'll sum all of the corresponding values. So we will have the total gradient, which will consist from the sum of all of the possible gradients for this particular neuron for multiple inputs. And this is what we did here. So it's kind of expand, and at some point we end up doing this. And I had one thing particular that's kind of wasn't able to kind of understand properly from the first time. So we're calculating, there are two examples. In the first one, we're calculating the partial derivative in respect to the weights and in respect to the inputs. And that's, well, biases, but biases is kind of the same. So with, where is it? So that was with the weights. And yeah, so this is for the weights and this is for the inputs and for the weights. And what I had trouble to understand is that we use partial derivative with respect to the weights in order to, well, weights and biases, in order to actually adjust parameters. We will take the fraction of this, but the idea that we calculate the derivative of the params to adjust the values. But also we're calculating the derivative of the input derivative with respect to the input values, and that will be the actual input for the, like, I don't know how to call it, for the next layer during the backpropagation. And the next layer during the backpropagation is kind of the previous layer if you read the network from left to right. I think I wrote it here. Yeah, so during the forward pass we're going from left to right, but during the backpropagation we're going from the right to the left, well, in that notation. And it means that we will start, well, in the end we'll be started from the loss value, going through the like activation function, and then go through all of the layers, and we will consider this kind of the next step. And what I did then, and we're finally getting back to code. So we have the dense layer, and what we need to implement is actually backpropagation, or the backward method, for relu activation function and for the dense layer itself. And I implemented this for the relu, because for the relu it's actually much simpler. Well, first we need to store the inputs that we had before, and we're storing the partial derivative for that input. So we're storing the inputs, and we're calculating the partial derivative. For the relu activation function, it's rather simple because the idea of the derivative for the relu is that the relu itself returns the value if it's greater than 0. So if we take the derivative, so the derivative will be, it returns 1 if the input value is bigger than 0, otherwise it returns 0. So it's rather 0 or 1. And then we had to, well, first we're taking the input, calculating this derivative, and then we multiply to the previous gradient. And the idea is that we actually can shorten it and just check if the input gradient, if the value inside the input gradient is less or equal to 0, we return 0. So it's just inverse condition, otherwise we return the value. And this is all we have for calculation of the backward for the activation. But for dense layer, it will be kind of harder to implement. So we have 3 things. We need to calculate partial derivative with respect to weights, with respect to biases, and with respect to inputs. And those values will be used for different things. And actually right now I don't understand that the only thing that should be private is the inputs. I don't need to expose it, but with others it should be public. Why it should be public? Because then we will take those values to adjust. By the way, maybe don't. Okay, I will see. I will return it as it used to be. So backwards, right? We have 3 things: gradients on params, and we have gradients on values, and so we need to implement the dot product between 2 matrices, the d-values and the inputs. And for the weights, we transpose the inputs and we take the d-values, and the result will be, almost forget what the result, I mean, in terms of, so first Okay, let me check again. It's not inputs. The first one is we take layer inputs, right? And here we take div values. And I want to find the code for the weights. Where is it? The weights inputs. Okay, so as the result for the weights, we have 4 rows and 3 columns. Well, let's talk about the rows first. We take in the transposed inputs. So we should take the number of columns, right? But here, number rows and the relu. Where is it? Relu outputs copy. Layer outputs. Okay, maximum layers output. Okay, the layers output, we take in the we take in the size. Number. Okay, we have the. Okay, from here we're taking number of columns and the number of which one is used relu. And that should be false. Then what we do? We doing this, right? But it's not the result. It should be layer the weights, right? We're taking layer the weights and what we're doing, we taking the weights, we're using product, and what will be the product for the weights? It should be input. What is inputs? Inputs is d values, transposed, and then we take in weights layer, weights. No. First. Okay, that's then with the biases. With the biases, it should be one. It's actually interesting. So we take in the product between inputs and no, we're using some layer. What is it? Deep bias equals math new dense and 1, then should be by number of the rows. By the sum of values to this over samples, first axis. The plain list. So we need to make a sum over rows. Need to make sum over rows. Right? So we have 2 dimensions, and then we go in so we need to go over the rows, and so for less than rows, then we take in values, and how we take in deep values row view, and do I have math sum? Yes. And math sum. And okay, this is then we get the bias. Non-indexable operands. Set one a plot. Not enough arguments to the call. Correct. Because I need I will know if I wrote everything correctly. I think once I will try to write something, but okay. So, and I need to write the inputs for I think this is similar to this one. Instead of inputs, we use the values instead of weights. Oh no, we actually use weights. Then we creating that's not the result, it will be layer. What we calculating? The inputs. And then we using dot product between then we use dot product between the values and transpose to weights, and that should work. Okay, let's take a look. I mean, right now we're just storing everything. So dense layer backwards. So we have the weights, we have the partial for the biases, and we have for the inputs, right? Then we have for activation. Let's take a look. So here we're finding the sum. And the backward is just... By this point we have covered everything we need to perform backpropagation except for derivative of the softmax function and the derivative of the cross-entropy loss. We actually don't have adjusting the values, because in this example we have it, the weights, but here I don't see something like this, but probably we'll do it later, right? Okay, so the next thing, well, yeah, maybe I will be able to record this one finally. If you are not interested in mathematical derivation of categorical cross-entropy loss, feel free to skip to the code implementation, as derivatives are known for common loss functions and you won't necessarily need to know how to solve them. That's true, you can find all of the derivatives. This is a good exercise if you plan to create custom loss functions though. Okay, I don't have plans, but I will check it. But I'm curious, cross-entropy loss derivative. Do I have cross-entropy loss? Oops. So I think it will be interesting. It will be values, dense, and targets array. Oh, and we will be actually storing something in here. Oops. Okay, but I want to check, well, at least I will start, and maybe I will finish for today with this one. Actually, maybe I will save it for tomorrow. I noticed this one. Actually, I can rewrite it. Does it still work? Yes. Okay. What I noticed is that, I mean, I can rewrite it, right? I can do the activation output equal to math, again, dense copy of inputs, right? And then I can do this activation output apply, and it will be func 0 for now, and it will be activation out and if I move it here, but instead return value, return 0, but it's not value, it's p. That should be the same. So this I'm just storing, and then I'm again making a copy, and I'm using the apply function, right? It basically should be like this. Yes. Yeah, just a small refactoring to make it, you know, proper go num thing. And I'm curious, maybe I can, oh, here is the same. Here probably the same. Variable. Okay, this video will be short because, as I said, I think I already spent around 2 hours instead of approximately 1 hour of recording, and I actually did a lot today. So yeah, next time it will be implementation, and we'll dive into what the category cross entropy loss derivative, how it's calculated and how it's implemented. Then softmax activation, same, it's actually way bigger. And then we will have the implementation of the backward. So common category, there are some common things, I don't know what it is, but it looks like a lot of the code. I'm curious how, I mean, at some point we should start full model code. Okay, this is the accuracy, and then we'll have the backward pass, and it will look like loss activation. Take the loss activation output, which is one value, right? Then we have the inputs, so we'll need to export them. Then we'll print the gradients, and ideally this is what how the training of the model will look like. But for now, let me get back to where I stopped. Not this one. this one again. Prosthetic loss. Okay. And I will double check tomorrow. Oh, probably I can test. I'm just curious about the backward. Probably, I mean, I'm not sure that I created the shape of the result matrix is right, but what I actually can do next time is, I can do the same, so I can use, like one forward pass on some dummy data and call those. I think this is actually what I will do. Let me put it to do. Func test backwards pass. And next time, next video we'll start from here and pass backward pass. This is what I will do, because I want to be sure, as it will be much harder to debug all at once, so I would rather debug the backward pass. For the rel activation function, it's clear, but for the layers, it's, I might mess it up. Again, thank you for watching, and I'll see you tomorrow. Bye bye.